Hey guys, this is part 2 of 5.2. We're going to revisit the upside down parabola area problem that we were doing in 5.1. So we're going to find the area under y equals 1 minus x squared between x equals 0 and x equals 1. So this time we're going to find the actual area. Last time we did it by approximating, and that's exactly what we're going to do to start with, except we're going to start our approximation with n rectangles. So with our n rectangles, I'm just going to kind of sketch them in here for pretend. And we'll go ahead and do a right endpoint method. So yes, I know n looks like, what, 7 here? But I assure you, it's actually n. So for those n rectangles, they will have width 1 over n, right? We've got the distance between 0 and 1 divided up into n sections. And what's the height of each of these going to be? Well, this endpoint is going to be 1 over n, and that'll be 2 over n, and 3 over n, and so on until the very last one at 1 is n over n. So the height of each rectangle will be equal to 1 minus 1 over n squared. And I'll put that on the outside. 1 over n quantity, not quantity squared, 1 over n squared subtracted from 1. So what does that look like for us? That means that the area of the first rectangle is going to be 1 over n times, this is f of 1 over n, right? Sorry, this is the height of the first rectangle. The height of the second rectangle would be 1 minus 2 over n squared, 1 minus 3 over n squared for the third rectangle, and so on. So the first rectangle is going to have height 1 minus 1 over n squared, and then 1 over n times 1 minus, keep doing that, there we go, minus 2 over n squared for the second rectangle, and so on up until the last one, which has width 1 over n and height 1 minus n over n squared. Now that's 1 minus 1, that's 0, but that's the area of that last rectangle when we use the right endpoint method. So let's do a little rewriting on this. Notice that the top number runs from 1 to n. So we can rewrite this as a summation as k goes from 1 to n of 1 over n times 1 minus. Each of these runs from 1 to n just like k, so that's going to be k over n quantity squared. So we could find the area for n rectangles where n is any positive integer just using this formula. And let's go ahead and do that. So rewriting at the top of the page here, the area under that curve, or the area estimate for n rectangles, I should say, is the sum as k goes from 1 to n of 1 over n times 1 minus the quantity k over n squared. Now we can do a lot to simplify this sum. This factor is constant with respect to k, so we can pull it out front. And now we can split this into two sums. So this is 1 over n times the sum as k goes from 1 to n of 1 minus 1 over n times the sum as k goes from 1 to n of Let's write that as k squared over n squared. I'm going to go ahead and pull out that n squared as well. 1 minus, so that'll be 1 over n cubed times the sum as k goes from 1 to n of k squared. And this is why we spent some time in the last lecture developing these formulas. I guess I should have written one more down here. The sum as k goes from 1 to n of 1 is equal to just n. So we need to use, let's see if I can't get them all on the screen at once. We're going to use this one for our first sum and that one for our second sum. So this is equal to 1 over n times, oops, not times the sum anymore. We're going to actually do that sum, and we just get n minus 1 over n cubed times this sum is, see if I can get it there. It's this one here. It's n times n plus 1 times 2n plus 1 over 6. So we have 1, when I cancel my n's, minus, we can cancel one of these n's and get n plus 1, 2n plus 1 over 6n squared. So now, let's go ahead and write that as not, we won't get a complete common denominator here. We'll leave it as 1 minus, we'll just FOIL out that numerator, 2n squared plus 3n plus 1 over 6n squared. So this formula gives me the area estimate for n rectangles using right endpoints. So if I divide this 0 to 1 up into any n intervals and then use my right endpoints, I will know that the area can be found by plugging in whatever that value is for n. Here's the cool thing, though. The cool thing is that the area is equal to the limit as n goes to infinity of a n. Right? The area gets closer and closer. The area estimate gets closer and closer to the actual area as n goes to infinity. Each of these little extra pieces that we're losing gets smaller and smaller. And so this limit is equal to the limit as n goes to infinity of 1 minus 2n squared plus 3n plus 1 over 6n squared. And that's equal to 1 minus 1/3, 1 minus 2/6, which is 2/3, as we predicted when we were looking at our chart back in 5.1. Well, this idea, this is the very idea of an integral, which I keep kind of teasing the idea. So this here is an example of something we call a Riemann sum, named for a mathematician named Riemann, who was he's famous for the Riemann hypothesis. Sorry, I just lost my screen for a second. He was a student of Leibniz, who is one of the fathers of calculus. And anyway, these Riemann sums are those area estimates. So let's figure out what a Riemann sum actually is. So a Riemann sum, I'm going to call it Sn, is equal to the sum as k goes from 1 to n of f at any point in the interval times delta x on that interval. So there is a neat kind of thing that we can do here. So let me give you a little curve to work off with. We'll say this is A and this is B. And so I can divide these up into rectangles, but I don't have to be as uniform as we were. Now, if you're going to calculate these, I recommend that you are, but this would be delta x1, and that would be delta x2. And so just because I have n rectangles, they don't necessarily have delta x equal to 1 over n, but they have, each of these has its own width, and each of these has its own height. And I can say on this first rectangle, choose a left endpoint, and maybe on the second rectangle, I choose a right endpoint. On the third, maybe I'll choose the midpoint. And on the fourth, well, it doesn't much matter. That one's pretty much the same. But I could choose a 3/4 point there, or whatever you call it. It's not really a 3/4 point, but you get the idea. And so I can set the height of these rectangles to be the height of the function at any point in the rectangle, because it's not going to matter so long as my delta xk goes to 0. Now, for our purposes, we will usually pick all delta xk to be equal to some given delta x, which is typically equal to b minus a over n. Not just 1 over n, but the whole width of the interval divided by n. That's usual, and we will also usually always pick left endpoints or right endpoints and not switch within a given problem. And we'll pick whichever one makes the problem work easier or whichever one we like better. It just really doesn't matter. So each of these Riemann sums is some area estimate for a function if it stays above the x-axis, but it doesn't have to stay above the x-axis. And I'm just going to show you the one in the book here to give you an idea. So the height of this rectangle would be considered negative. It would have a negative height. F of C2 would be whatever that value was. And so it's not exactly an area then. It is, in some books call it a net area. It would be the area of this part of the curve minus the area above that part of the curve. So how will this work out for us? So let's take and say that Sn, this will be for right endpoints, Sn would be equal to the sum as k goes from 1 to n of f of, we'll just call that guy xk. He'll be that one, that one, that one, times delta x, where delta x equals b minus a over n, and xk equals, this one's a little tricky here, but it'll be equal to a plus b minus a over n, that's my delta x, times k. So when k is 1, I will move over 1 delta x from a, and that's my right endpoint. And when k is 2, I'll move over 2 delta x's. This is sometimes just a plus k delta x, because that's easier to write. So that's how we would write a Riemann sum for right endpoints. We could put that in as the sum as k goes from 1 to n, f of a plus k delta x times delta x. And so that's where we've picked our intervals to all be the same width. So we're just picking n rectangles that all have the same width. And then we're setting the height to be the height at the right endpoint of each of those intervals. That will not always be an underestimate. If you look at this guy, the right endpoint here would be a taller rectangle than a left endpoint. It's going to depend on whether the function is moving up or down. So a left endpoint here would be 0 and shorter there. But if I do a right endpoint instead, then there's the right endpoint rectangle, there's the right endpoint rectangle. But then as it would come back down, right endpoints would be smaller than left endpoints. We can do the same thing for left endpoints. Let me show you how the formula changes for a left endpoint. So for the left endpoint, we really can just think of it as the same as the right endpoint. We still want delta x to be equal to b minus a over n for uniform rectangles. But then xk now equals a plus b minus a to the n times k minus 1. And all that does is when I take x1 now, instead of adding one of these, I'll add 0 of them and I'll stay at a. And so then x2 will add 1 delta x. So that's a plus k minus 1 delta x. And then our Riemann sum for left endpoints would be the sum as k goes from 1 to n, f of a plus k minus 1 delta x times delta x. Probably at this point you're thinking, well, right endpoints are obviously superior to left endpoints because right endpoints just have a k and left endpoints have a k plus 1. And I don't think you would be wrong. I think if you have to pick, almost always getting to pick right endpoints leads to an easier summation. I'm sure there's an exception to that as a general rule, but it's been my experience that right endpoints lead to easier summations than left endpoints. That's not the end of the world. It's just a -1. We can take care of it. But yeah. All right. Well, that's all for 5.3 part 2. It's really just an introduction to the notation of a Riemann sum. Now, I used SN, which our book uses some of the time. There is another more formal way to say this, but it almost never comes up in a regular calc class. And that's what I was talking about at the beginning, that we don't have to let these intervals be uniform, in which case, instead of just saying, hey, we want n to get big, we have to say that we want the biggest distance of all of these to get small. And so you can read about that on page 316 if you're curious, talking about the norm of the partition, which is really just the maximum width of an interval here, is how we're defining it. That's all for 5.2. See you guys later.